final project. So thank you all for being here today.
I have no idea. How does one do this? Maybe.
Oh yeah, you're recording already. Perfect. And then the screen needs to turn on.
Oh,
I love the shirt. Thanks. Gotta zoom to what? Sure. Final project. Okay, slay. For this.
good question. Great question. Oh.
Okay. All right, so today, like I said, we're going to be developing our field with Pandas, which we will introduce in a couple of minutes. Announcements. Homework 5 is due tonight, I believe. Question mark.
Yes.
Yeah,
it is.
Homework 5 is due. Homework 6 will be dropped ASAP. And we're going to talk about final project rehearsal right now.
Just an FYI, there was an original homework schedule posted on B courses, and then everything got shifted downwards. So it's updated now. So all the dates on there should be correct. Yeah, so basically we're just going to go through the final project proposal today. It's linked on B courses. If you just go to files and then final project, I'm just going to do it on here because it's a little bit easier. But basically the whole point of the Python decal final project is to compile everything that we taught you into like one cohesive final project. And it should be something that you're really interested in. So like some sort of like astrophysics or physics related phenomenon. It doesn't necessarily have to be related, but it makes a little bit more sense if that's your major and it's related because it teaches you a lot of good skills. Yeah, basically, you pick a phenomenon that you are really excited about, and a lot of the times, like it's really common to do like some sort of animation or some sort of like data analysis. Yeah, it's kind of like very open, and we like to leave it that way so that you guys can do something that you'll use in the future. Like this is something that can definitely go in your resume and probably should go in your resume. And also like it doesn't have to be absolutely perfect when you do it in this class because we know it's a super limited timeline and it's hard to do a really perfect project in the amount of time that you're given. Like I'm still working on my project that I started from the decal. So as long as you have some cohesive project that you're working on and you have some sort of output from it, then that's a good project. But it's something that you should definitely like keep working on in the future if you want to, if you don't finish it. But yeah, the criteria for it is it's a 1 to 2 person project. And you're gonna have to be able to generate some sort of test data. So you need some sort of random test model to verify that it's producing a reasonable result so that even when you just run random data through it, just to make sure that your code is working. And then after that, you'll use data from an existing set. And then data quality and reduction, that's kind of what we're gonna go over with like curve fitting and stuff like that. But basically you want to apply like a quality filter. So when we go over pandas and stuff like that right now, you're going to essentially like sift through a lot of the tables and take out variables that you don't want. Because a lot of like astrophysics data comes with a lot of unnecessary variables for what you're doing. And just be able to like explain essentially why you're taking out certain variables. Like if you're finding Hubble's constant, explain why you don't care about a certain flux in a certain band or something like that. And then model fitting. So essentially, I think that's next lecture that we're going to be teaching you how to do model fittings. So you're going to be able to perform a fit of your model to the data, including error analysis, because data doesn't mean anything if you can't explain it and show your results. And that has a lot to do with graphing. And then model explanation, basically essentially being able to explain why your code works and what it does, and what you learned from it. And then your report is going to be a 2 to 3 page report detailing your work. That's super straightforward. Not really any flowery writing, just basic standard science writing. And then your presentation. It's going to be a 3 to 5 minute presentation about your final project to share with the instructors in the class. That's going to be on December 3rd and 5th, and the timeline is detailed later. Okay, so the proposal is going to be essentially outlining how you'll address all the items that I just listed before. So That's the test data, data quality, model fitting, model explanation. And it's just essentially like a rough outline. You don't need a super concrete idea right now, but just a general idea of how you would go about that. But yeah, you should look into the source of the data. Also doesn't have to be super concrete, but if you're going to be pulling like Galaxy data, well, you can use DESI, maybe. Yeah, DESI might be a good example, but that's a little tricky. It's a little tricky.
When Katie took the talk, I threw the DESI database at her and was like, "Hey, figure it out." I helped her figure it out. Didn't I?
Sort of.
Okay. Well, figure it out, basically.
And
Yeah.
we'll be here to guide you along the way.
Yeah, a good part of this project is basically we throw you under the bus a little bit, I'm not gonna lie, because it's it's a big task. But it's really good real world experience with like sorting through data, because nobody stores their data in a great way. It's pretty awful.
Which we will see later today.
Yeah, we'll figure it out.
Also, at some point today, I'll post on B courses in the final project folder. There's this like really nice compiled guide of a bunch of places you can get data from. So I'll throw that on there. That could give you inspo. You could be like, oh, this website's cool. I could get data from here. Backtrack, what project can I do?
Yep.
So that could be helpful.
Yep. Okay, yeah. So once you figure out like what source you're getting data from, how you filter that data is going to look super different. So that's just something to keep in mind. And then obviously putting all the names of whoever's on your project. Something to note though is that only one proposal is required per group. So you don't have to submit 2 proposals if you're doing a group of 2. Okay, so for your project, basically, you're gonna essentially just do like flesh out what you did on your project proposal, just in more detail. It's similar to like future homework assignments and whatnot. But like I said before, generating test data, fitting the data, and then fitting the data to from external sources. So like you have your general model. Like if any of you have taken C10, I did my project on the Hubble, not like calculating Hubble's constant, and I used one of the lab data from that class because it's really good data and it gives you a nice solid line. So like that would be an example of like test data that you can run through it and make sure it returns a reasonable answer. And yeah, making sure that your project includes plots and displays your data from both the fitted model and the data that you pulled with error and everything. And make sure that when you present, that's clearly displayed as well.
Quick thing about the partner thing. When you submit your project proposal onto Gradescope, if you have a project partner, you can like add their name onto your Gradescope submission. Make sure you do that so like your project partner also gets credit for your work.
Okay, you do that through GitHub, or is it just through?
It's just through Gradescope.
Okay.
You don't need to submit all this stuff via GitHub. You can just do a normal file upload on Gradescope, how you would submit normal assignments.
Okay, the report, again, 2 to 3 pages long, and it's basically just a summary of your project work. It should be an overview of your methods, any Python libraries that you use, theoretical concepts that you applied. It's pretty similar to your project proposal, but with a little bit more detail, like a just basically more fleshed out version of it. But yeah, you shouldn't copy and paste. You can use it for like reference, but it's better to just flesh it out because usually a lot of this stuff changes. The proposal is more of just like a good idea to head in, like a good direction for you to head in versus the final output.
Also, as instructors, we will all be reviewing your proposals and giving you feedback as to like how feasible it might be, if we have any suggestions. So like try to put as much detail into it as possible so we can like guide you in the right direction. And if we feel like the project's not feasible, we'll be like, hi besties, maybe similar topic, different approach, something like that, just because we want to make sure you can actually get it done on the timeline and it's not like stressing you out too much.
Okay, and then finally for your presentation, it's just a 3 to 5 minute talk to share with the project and class and instructors. As again, it's just an overview and then a summary of the methods you use, key findings and data analysis. So basically detailing what Python you used and your results. And then highlighting any interesting results or insights that you discovered and discussing the significance of your work. Yeah, visuals are super important. We like graphs, as we will learn today. And then don't just like have your entire report on the slides, like try to like have an actual presentation and like verbally say it instead of just having a lot of words on the screen. And yeah, like a big part of the presentation is it honestly should be kind of fun. Like choose something that you're excited about so that when you get up here and talk about it, it is something you genuinely enjoyed doing and are excited about. And yeah, for the timeline, we just did the introduction. I forgot to change that date. It should be 10/29, but the rest of the dates should be correct. It is due on November 10th at midnight. And then we're gonna have, is this the wrong? This is the wrong. 1 second. Did I? Oh, okay. Okay, this is the right one. The one posted on B Courses is correct. No, it's not. JK.
We will fix
Wait, no. It is. I'm sorry. I read it wrong. It is due on November 10th at midnight. And then we're gonna have one work day. I believe that's the Tuesday of Thanksgiving break. So if you guys are out of town, don't worry about it. If you have any questions from that work day or anything, just feel free to shoot us an email. And then the final project is due December 2nd. So that's the day we get back after Thanksgiving break. That Monday, I believe. And then presentations are the following Tuesday and Thursday. That's the last week of instruction. Okay, cool. Okay.
All right, so that is basically it for final project, but if there's any questions, feel free to like let us know. A little bit of a recap for what we've been doing the last couple of lectures. You guys have explored NumPy and hopefully have gotten super familiar with it by the discussion, by the homework. And so now we're going to see that now we have all these functions, right? We can like take a minimum, we can take a maximum, we can average, we can do a standard deviation. What is the point of all these functions if we do not have data to use these functions on? So what we're going to learn is how to load in that data, how to grab data from the internet, how to like process data, fun times. So caveat with data. Data in the real world is really funky and different from like a nice little data table you see in your textbook. Because number one, especially when you're working with scientific data, like from instruments, there is a lot of data, especially for like missions that have been going for years and they're like taking a recording of a timestamp that's like 12 seconds apart or something. You're going to get so much data, like tens of thousands, hundreds of thousands of data points. And number two, it's usually messy. And the reasons that it's probably messy is because this is real-time data, right? Like nobody's able to like be up on a little telescope and like fix it the moment like something like goes wrong. And no one's tracking it as every single data point's coming in. So there will be fluctuations because of like natural things happening. Also, there's probably going to be some errors with instruments. There might be little fluctuations. Sometimes the data is just not structured correctly. It might like come out as like a list of numbers and you're like, I don't know what these numbers mean. And it is up to us to be able to parse through that data, process it, understand what it means, and like organize it neatly before we use it. I'll show you an example. This is a data set I use for my research. It looks very complicated, and that's because it is. So this is data from one day of the entire year from this instrument called MIGHTY. And you can see that on one day, there is 7,594 data points. Every single data point has a date time and an altitude. So this is like a multi-dimensional set. So if you multiply those three numbers together, that's actually the true number of data points. And then it also stores all of this information for every single one of the data points. So this set right here you're looking at is like for one day about like 10,000 data points. And I run analysis on 2 years of data. So you got to learn how to work with things, and that's what we're hoping to teach you. So as like a little introduction to what we call exploratory data analysis, I posted this link on Ed. So I want you to open it up super quick. So this data set is a salary survey, which is from a website called askmanager.com. It's literally a live data set. So people can go fill out a little Google form and the data set on the website gets updated. So it's a really good way to see like literal data being produced live. There are a bunch of different features in the data set. Once you pull it open, you should be able to see that there's like a bunch of variables like age, industry, job title, et cetera, which all have to do with someone's salary. And there's different types of data within the data set. You have free-form text entry, which is like people like typing a little free response, but you also have like categories where you can select like an age range, a salary range, et cetera, et cetera. So what I'm going to ask you to do is this quick exercise. With the people on your table, look through this data set a minute or two and come up with 3 ideas on how you could use the information on this data set to like come up with a conclusion or like make it more usable or make it more readable, something like that. So take a second or 2 minutes. I can't give you too much time, but like take a minute, please talk to each other, and we'll go from there. I forgot what my answers to these exercises were, but that's okay.
Do you want to take a look at it?
It's in speaker notes. I can pull it up. Okay. Bringing us back, do people have any ideas? You don't need to have 3 ideas, but shout out if you have an idea of how to like clean up the data set, make it something that's more like parsable to our brains and information that we could use better. Any ideas? I'm seeing no ideas, and I find that very not believable. Yes, what's up? Yeah, exactly. So for example, if you guys look at the currency column, a bunch of people's salaries are in different currencies, which means they might have like someone might be being paid $100, someone might be being paid like 100 rupees, and the number 100 is the same, but the currency is different, which means their like salary is different. You don't usually want a discrepancy like that in your data set, right? You want everything to be like the same metric. So yeah, currency conversions is one really, really good example of that. Other things is like, if there's categorical variables, you want to like group people together based on their age range or based on their salary range or et cetera, et cetera. Those are all things we can do. This kind of ties into the same one. I'm gonna like gloss over it because we don't have much time, but when you look at a data set, the first 2 things you want to do is number 1, try to figure out how you clean the data, and number 2, you want to try to figure out what questions can you answer using this data. So for example, something that's very, very common to look at when you have a data set, you want to see how someone's salary relates to where they live, or someone's salary relates to how many years it's been since they graduated, or what kind of degree they have. So you have all that data, and what you're trying to do is form connections, form correlations, because that's the way you're going to draw fun conclusions from your data. And that's kind of like the entire concept of what we call exploratory data analysis, which is basically the crux of your final project. We just did it. It's basically a process that basically anyone that works with data, so like scientists, data scientists, econ people, everyone like that, biologists have to work with this process, because you get a bunch of data and you're like, I'm looking at numbers, I don't know what they mean, and you want to extract some information from those numbers. So that's a big takeaway from what we want to show you.
Okay, so so far we don't really have the tools to like pull some data onto our computer and then organize it and view it in a way that is nice and pretty and not absolutely awful. So Pandas is a really good way of basically being able to pull data and put it into a Pandas data frame, which essentially is just a display. It's just a table essentially of viewing it. So yeah, it just makes it super clean and fast and convenient in Python, because you can index and emit rows and columns and stuff like that fairly easily. And it adopts a lot of like coding idioms from NumPy. So like I just said, a lot of like indexing and stuff like that, like arrays almost. And the biggest difference is that Pandas is designed specifically for working with tabular or very uniform data, or no, that's the opposite.
Structured.
Yeah, essentially structured data. So it works really good if you have some sort of like CSV file that is already in a table. It just needs to be read off and put into a table that's in code. So Pandas is really good for that. Okay, so essentially you can have kind of how I mentioned before, it's kind of similar to arrays. You can have a series, usually denoted by pd.series. A lot of the time in, you know how we did NumPy as NP, PD is going to be the same thing. Pandas is just going to be PD. So a series is a 1D labeled array data. So it's just one column of data. And a data frame is going to be both rows and columns. So that's going to be like your 2D matrix or array. And then indexing is a list or sequence of row and column labels. So if you have 5 different rows and you just want to take the first one, it's going to be the same concept of indexing that we had going on with arrays. Okay. So if you guys want to open up Jupyter and follow along.
The
For a
file for
demo.
this is on B courses, so you can like literally follow. Yes.
Yeah.
0. Everything in Python always starts at 0. But yeah, starts at 0.
Sorry, it's going to take a minute to load because I have like 60 tabs open. What's up? It is, here, I'll show it. If you go to files and then demo code, it's going to be the first one, data frames demo and sample data CSV. Just download them and put them into a folder that you can keep track of. So like your Astro folder would be fine, like folder for this class.
Yeah, just make sure they're in the same folder. Otherwise your computer, you'll have to like specify the whole file path, which we don't need to bother doing. Okay.
Okay, since we want to use pandas, we're going to import pandas as PD, like I mentioned earlier, and then import the normal stuff. So import NumPy. And then we're going to import matplotlib to make plotting easier. Did we go over that?
We haven't, but we'll,
Okay.
actually, I don't know. We might have. Can you make it?
Oh, yes.
Also, if you want to make this faster, you could also just use the skeleton code that's on the courses, because then you don't have to type out the whole dictionary. You call them.
Oh, it's okay.
Okay,
I'll just go really fast. Okay. Okay, so you could pull this from B courses, but I'm lazy, so I'm just going to type it out really quick. I'm just going to make a dictionary real fast of some like arbitrary values that we're going to put into a table. So we just got a list of our dictionary of fruits.
And for those of you who downloaded the demo file, this is on there already, right? Okay, slide.
You see, I could just pull that, but
and like in this part, especially note the structure of the dictionary. You have a key and a value that's separated by the colon. But here you see how the value is a list. You have multiple values under a key, and that's going to be super important because we're making it like rows and columns. So also, you probably will never really create a data frame from scratch. That's not something you do super often.
why is it not liking this?
Unless you're like
Nope.
Doing like data collection. Yeah, unless you have to write a script for data collection. If you're just doing analysis, you don't really usually do this. But sometimes you might write data collection scripts, so it's good to know.
Okay, so to run this, we're just going to do pd.dataframe and then in parentheses data. So basically what that's telling, what we're doing there is we're essentially running a command to make a pandas data frame with a specified set of data. So in this case, it's a dictionary that I wrote out, but like in the future, it's probably going to be a CSV file or a text file or something like that, that you would essentially just put in the quotation marks and run it like that. Okay, great. So that gave us a pandas data frame with everything that I put in the dictionary, which would be fruits, colors, and sports. Very vital things, apparently. Yeah, does anybody have any questions on that so far about how it organizes it?
Also, quick thing to draw your attention to, we did not put in 0, 1, and 2 here when we specified our data frame, right? We just put in like the names of the rows and then names of the columns and then the like data inside it. 0, 1, and 2 are the example of row indices like we were talking about before. So PD index, those would be pandas indexes right there for the row.
Okay. Okay, so now we're actually going to pull it from a CSV, not CVS file. So we're going to do something similar. We're just going to set data. Actually, we're going to call it data 1 for coding etiquette. And then we're just going to essentially read off the file. So pd.read _ CSV. The CSV is an important note because if you're going to pull from like a text file or some other format, you have to tell Pandas what it's reading. Otherwise, if you throw a text file in there and you tell it to read a CSV, it's going to scream at you and go, that's not a CSV. And it's going to mess up all your data and your table won't look pretty when you spit it out. So that's another important note. When you're looking for data for your final project or just in general, you need to make sure you know what kind of data format it's in for that exact reason. Otherwise, you can't read it.
And to add on to that note, you can use read CSV for text files, but what you're going to have to do is find some optional parameters that make it work, and you can look at the documentation to do that.
Yeah. No.
The sample data not exist.
I downloaded it.
Is it in the same directory?
Okay.
Okay,
I have to dig through my
Why
file.
don't you just hit upload and put
It's probably, oh, here.
E? Because then you can just manually.
Okay, also a good learning moment. I messed this up and I downloaded the data before class, but I didn't put it in the right folder. I put it in Astro Demo, where is it?
Right there, sample data.
Yay. Okay. So yeah, that's just a note that if you're pulling data, you have to make sure it's in the same folder that you're running on Jupyter. Because I didn't do that.
Good thing though, Python will yell at you and tell you it doesn't exist.
Okay, yay. Now it likes me again. So yeah, we have a really nice data frame. As you can see earlier on B courses, when you pull it up, you can't really see anything and it's like on a PDF and it's weird. And you can't really work with that if it's on a PDF, if you're trying to run code with it. I mean, you can, but it's not fun. So yeah, this is a really nice and convenient way and you can index it and do whatever you want with it now. Okay. So back to the slides. Okay. So essentially, what we did there, just quick overview of that, is creating a data frame. Yeah, we created it from scratch, which is possible, but we don't really do that a lot of the times. But the common thing is loading up a data source like a CSV file. That's going to be the most common one. And then, yeah, there's,
No, that's good.
Okay, don't worry about that.
Okay. So now we know how to load in our data. Our next step is to figure out how to index and access our rows and columns, because now we have all our data in a pretty table, but we want to like do certain operations on certain rows and columns. We need to know how to access those specific data points. This link right here is like it'll go up on B courses, but if you guys ever get stuck with what I'm about to explain to you, it's just a really good reference. Cool. So very similar to how we do NumPy arrays, where we like slice, which is like, you know, how you can get element 2 to 5, et cetera, et cetera. We can do the same thing with pandas with a data frame. One caveat though, we have to remember that there are both rows and columns. So when we are indexing, we need to be very specific about what we're doing and whether it's rows or whether it's columns. Pandas has two inbuilt ways to do indexing. One is using .lock, and the second is using .ilock. The way that I like to remember the difference between these, .lock is label based because it starts with L, and .ilock is index based because it starts with the letter I. And I'll show you a demo of how both of these work. Sorry. Are these little things visible in the back? Or not really? Not really. Okay. I don't know if you can zoom on a slide.
Oh, here's what we can do. Exit like this.
Okay. Oh, slay. Wonderful. Perfect. Okay. So what df.lock does, you can put in a set of like row or column labels, and then it will output whatever row or column it is. So an example here is if you have this data frame where these are your row labels. Typically, like we saw in the dictionary we created, these were those numbers 0, 1, 2. So usually your row labels are not actually words. They're usually integer values. So like, for example, here, my row labels are actually the numbers 0, 1, and 2, which gets a little bit confusing because you look at them and you're like, wait, those are indexes. Like in your head, those are not labels. But good way to remember it, if it's in bold, it's a label. Like that's how you can think of it. If you have a Pandas data frame and it's in a bold format where you see like fruit, color, sports, 0, 1, and 2, those are all labels. Does that make sense? Okay, cool. And I know there is a way to specify row labels. I am just not covering it because usually we do not use it because a lot of times you're just like row 0, row 1, row 2. There's not usually specificity to every single row. Okay. So in this case, we did df.lock at Viper. Viper, you can see, is the name of this row. So what Pandas will do is output the column values at Viper. So it gave you that the max speed at Viper is 6 and the shield at Viper is 5. Now, let's look at ilock. So ilock, again, I said was integer. So it's index based. Instead here, this looks a lot more familiar, right? With the 0, 1, 2, because that's kind of what we have going in our rows. So very similarly, instead of using a label name, you're using the integer value. So this is row 0, but also remember row 0 has the index 0, but it also has the label 0. That's the weird, funky, confusing part. And when I show you the demo, hopefully it'll make more sense. But here, when you do .ilock at 0, you're going to get all the values of all the columns at the given row. Now you guys might be like, oh, wonderful. Now I know how to get specific rows. How do I get specific columns? And we will go into that in the demo. All of these slides are more like specifics on how lock and ilock work. You can reference them on the B-Courses page, but I would rather just demo it so you guys know. Did you download the demo file off B-Course at all? Okay.
It's probably in the wrong spot again.
That's okay. Let me try to find.
It's
Would
not
it-
gonna be in there. It's
Okay.
gonna be under it's this guy.
Astro 98 demo, which is hiding in Astro 98, which is here. Okay, perfect. What did I even call it? Okay, data frame demo. Okay. I was like, oh my
I
God,
also have all the ones from last semester.
that's so real. Okay. So now I'm going to walk through lock and ilock and show you like more use cases of it than just the simple like one variable use of it. Okay. All right, so this data frame should already have been given to you guys, but it's constructed in a very similar manner to what we did earlier, where it's like this label, that's the column name, and this is all the data in that label. So now I have this data frame, and yippee. So like we talked about, lock is label based. So my first example, I might like show you one example and ask you guys how to do another example. But let's say I want to get this point. I want to get the year 2014, which is when this brand, I don't actually fully know what this data set is. I think it's just for cars. Let's say I just want to get this year 2014. Using labels, does anyone have any ideas for how to get that singular data point? Because we know how to get the row, right? Can someone tell me how to get the row? Oh, that's fun. So that's great. She's stable again.
I guess I just have to hold this.
Is
Maybe
it
if we
really? Can I just like let it
Oh,
go?
there it
Okay.
goes. Yeah.
She's fine. Okay. Now that we've had a second, can anyone tell me how to get the row 1 using dot lock? It's okay if it's wrong. I just want to see if people have ideas. Any ideas? Yes. Mhm. Yeah. So the data frame is called data. So I'm going to do data lock, use, like you said, the square brackets. And to get row 1, the label for this row is 1. So I'm just going to do that. So what that gave me is all the information in row 1. That makes sense, right? But now I specifically want the year of row 1. So the way I'm going to do that is do a comma and specify year. Oh, I clicked a button. I hope that doesn't
It's
screw
okay.
me over. Okay.
No, you're good.
Okay. So now when I do this, I get the number 22. I get the number 2014. Does that make sense to people? I said I want the information at row, which is labeled 1, at the year column. Intuitive-ish enough? Okay, cool. So now that's just for one single data point. So that I'm going to put right here because that's for a single point. So you get 2014. Now let's say I want to arrange rows and columns. Let's say I want all of the, let's say I just want all of the years. Like I want all of just a list of my years. I want a series. Way I can do that is saying data.lock. And this is something that you guys are going to have to get a little used to, is if you want all of something, either if it's all the rows or all the columns, you just do a colon, which tells Python that's everything, all of the rows. And anytime you do an index, it's always going to be in the format row column. So here I'm saying do all of my rows and give me the specific column year. And now I have this nice little Pandas series of all of my years from 2012 to 2019. And I could change that to anything. I could change that to city as well, and I would get the entire column of city. So that's going to give me all of my cities. I could also switch this around. I could do all of my columns at a specific row. So this is saying at row 0, give me all of my columns, which are brand, year, kilometers, city, mileage, etc. Cool. And now I'm going to just switch this back to this because I like it more. And now my next part is if I want to specify both rows and columns, how would I do that? Well, same way that you would typically index by rows and columns. You can say, I want, I don't know, I guess row 3. Or like, let's say I want rows 3 to 5, and then I want the column city. So what this is going to do is give me 3 to 5, the labels 3 to 5, and then it's going to give me the cities in those labels. Does this make sense to people? Yes. So it's inclusive because these are labels right now. We're not working with indexing right now. The confusing part of this is right now 0 through 8 here are labels. They're like integer labels because a label can be anything. They're still integers.
I think what he's asking is if like why isn't it and also in quotes?
Oh, okay, I see. Well, because the data type is still a number, like it's still an integer, but you can use an integer as a label. A label doesn't have to be a string for pandas. That was the thing that I was mentioning that was a little confusing earlier, where it's like these are integer indexes, but they're also labels. So yeah, and I'll show you like explicitly like the difference when it comes to like the index-based system, and it'll become hopefully a little bit clearer. But here we're basically getting getting the rows labeled 3, 4, and 5 because we said 3 to 5, and we're getting city. And then one other cool thing you can do, this one I will walk through as quick as possible, but you can also like use lock to impose like a condition. So I can do data.lock, and let's say I want all the data where for a specific brand. So I could do data.brand, because that's the name of my column, equals because I'm checking for equality, and the name of a brand. LOL. It's because I messed up my parentheses. Okay, cool. So now it gave me only the rows I want where the brand is the brand I specified. So this is something that's super helpful because then you can get whatever rows that correspond to current whatever data values. You can also chain multiple conditions. So here I said the brand is the specified brand, but let's say I also want only the brands where the mileage is above a certain number. I can do where that the brand is whatever brand I give it, and then I do data dot mileage, because that's my mileage column, and you can say greater than, let's say greater than 26. So we get rid, technically, if this code works, this column should, or sorry, this row should disappear. That makes sense, right? Because you want the data to be both the specified brand and above the certain mileage threshold. And that's exactly what happens. So that's how you impose conditions on your data. Does that logically make sense? The syntax might be weird, but I will post like a completed version of this so like everyone has access to like go back and mess with it. Okay. Now, this was all using labels. Like we saw, we were using like string names, and we were using integer labels. Now let's move on to actually just using indexes. And then hopefully here's where the difference will become a little more clear. So now let's say I want to have, I don't know, I want to select rows, these first couple rows, 0 to 3. And then let's say I want to select the first 3 columns. And I want to use index-based labeling. I could do that doing data.ilock instead of lock right now. But it follows the same structures where you specify rows and then you specify columns. So I would specify rows 0 to 3, and then I would also specify columns 0 to 3, because I think that's what I said. Notice how here, when I said ilock, my rows are 0, 1, 2. And that would differ from the previous case. Like here, if I gave it 3 to 5, if I'm correct, it's disclusive here. Does that make sense? Because now we are using indexes. We're using actual like integer indexes and not labels. And I know it's confusing for the rows, but hopefully with the columns, at least it like becomes a lot more clear and intuitive, because I'm getting these columns brand, year, kilometers driven, which are brand, year, kilometers driven. Okay, slide. So that's how ilock works. You can do the same stuff you were doing with lock that you were doing with ilock. Something that's also fun that you can do is also give it like a list of rows. So you could do like, I want these specific rows, and it'll pull out those specific rows. Okay, so that is lock and ilock. Also, sometimes you want like a little shortcut. You don't want to type out like all of this stuff to get a single column. Let's say you just want to like find the min or find the max of a specific column. You can just get a single series just using a bracket. So I can use data at, I don't know, let's do MS driven. And that will just output that one series. This is super useful because sometimes you can like, let's say I want to assign this a name. Let's say I want to say this is kilometers. And then I want to find like the average number of kilometers that's been driven by all these vehicles. You could just do np.edge kilometers. And that gives you the average. Super helpful tool. Also, every single one of these operations results in like a mini data frame. So you can still access individual columns and rows in this mini data frame if you save it to a new data frame. So I could say this is like new df, for example, and then I could like say new df at brand. So new df at brand exists. But if I did something like new df at city, because city's not in this new df, it's gonna like yell at me. Because it's like, what, there's no city in the smaller subset of the data frame that you created.
Quick thing that it gives, if you only do a series, it's not a data frame, correct?
Yes.
Yeah.
Correct.
Um,
So
So something to know is that if you saw earlier when it didn't give us a data frame, that's when we're only doing one column. That's a series, and that will not give you a data frame. So if you were asked on a homework or something to create a data frame of only one column or one row, like that's not a data frame. You would have to then put PD in front of that and make it a new data frame.
yeah. So right now this is a Pandas series. You have to convert this back into a data frame, which you can do is like, it's like a pandas.2 data frame or something. And now since we have a couple minutes, I just want to make a quick familiarization for people of the Pandas documentation. If you just look up Pandas documentation, it will take you to this thing, which shows a bunch of stuff that exists in Pandas. We are most interested usually in data frames. These are all of the functions that you can do on a Pandas data frame. So crazy amounts. You will get familiar with some of these via discussion, but if there's like anything that you're ever like, I have no idea how to use this, you can go look at this API page or this reference page. And I'm going to take like a couple minutes. I don't know if this has already been done, but just in case it hasn't, I want to walk you through the structure of a general like reference page or an API page, because you will be using this. When you don't know how to use a function, you're going to look it up and this is going to pop up. And then you're going to be like, I don't know how to navigate this. There's so many words. So I'm going to show you how to do that. And I'm going to do it with a NumPy function that we're familiar with, just so it makes sense. So I'm going to just look up NumPy max. So this is a nice little NumPy function that finds the maximum. So this is usually the structure of the page. It'll give you the name of the function because you looked it up. And then it'll give you the function structure. It'll say numpy.max, and then these are all your different input parameters for the function. Usually when we do a max though, we don't put all these things in, right? Like what is access, what is out, what is keep dimmed, what isn't, like we've never seen that stuff when we use it. But these are all things called optional parameters, which might be useful in certain cases. Usually what we do is put in an array because you want a max of a set of numbers. So it says your parameter is A, which is array-like, which means anything that's in the form of an array. So like a list, a NumPy array, all of those things, or a Pandas series, those are all array-like structures. And that's your input data. And then you have this parameter called axis. So this is super helpful if you have two axes, if you have an X and a Y, like in your rows and columns, or like in your little NumPy matrix. Let's say you want to average across the rows, or you want to average across the columns. You want to specify what row or column, that's when you use axis. So then you'll see how all of these are labeled optional, so you don't have to use them, but they might be helpful. And then at the end of this thing, you will see some examples of how the function's used. This is, to me, the most important and valuable part of a documentation page, because it really shows you like, hey, this is what you can do with this function. And here are some examples. And you will truly notice on the NumPy and Pandas homework how much you will use these documentation pages. So I wanted to introduce them also before the final project, because I'm sure people are going to be using functions that none of us have heard of. And then we're going to have to walk through this process basically with you. But here's like a little insight onto how we program, because none of us usually know how to do things. Yes. How do I get to this page? I just looked up on Google like NumPy max, and it's like usually the first thing that shows up. But if you want to like explore functions, you can just look up like a certain documentation, like Pandas documentation, for example. And yeah, so you want to usually, it's easier just to look up a specific function. And then you'll see like a nice structure where you can go to all the little things. Otherwise, you have to go to the API reference and then pick what structure you're working with. So for example, Pandas, you can look at the series, and then these are all the functions for a series. But yeah, that's it for today, I'm pretty sure.
Huge part of Python coding, and because Python is open source, anyone can make a document.
I can walk you. But yeah, I'll post the like solved out version of